Hello everyone, welcome to my civil engineering YouTube channel. Please subscribe to this channel and hit the bell icon to get notified when I post my new videos. So today I'll be discussing how to determine the radius of gyration as in case of channel section. So this channel section, in short, it is also called as C section or C-shaped section. Okay, so here I have a numerical over here. So here we need to find out what is the least radius of gyration as in case of this given C section. So here the top flange is having the width of 120 mm and depth of 100 mm. So the web part this is a web part. So it is having the depth of 100 mm. So total is 120. So 120 minus this 10 and 10, if I do, I'll get the web part. So web part depth is equal to 100 mm. 120 minus 20 will be 100 mm. And then width is equal to 12 mm. So bottom flange width is equal to 180 mm. And then its depth is equal to 10 mm. So we are supposed to determine what is the least radius of gyration for this given C section here. So this is the centroidal axis for the individual structures. So wherein I am just dividing this individual structure into three rectangles. So this is first rectangle, and this is second rectangle, and this is the third rectangle. So wherein I have assumed the x and y axis. So with this reference to the x and y axis, I am supposed to find what is the moment of inertia about both the axes. So I need to determine the moment of inertia about both the axes since it is unsymmetrical section. So therefore I need to determine the moment of inertia of both the axes. Upon that, in order to calculate the least radius of gyration, so I need to determine for moment of inertia for x as well as y axis. So here you can just observe that I have considered the three individual rectangles 1, 2 and 3 whose centroids are G1, G2 and G3. So here first and foremost thing is that the step 1 is I need to determine the area of the individual figures over here. So the first figure is that the area will be equal to 120 is the width and depth is 10 mm. So it is equal to 120 into 10. So it comes on to be 1200. So second sketch is that the second figure with the web rectangle whose depth is equal to or whose vertical dimension is equal to 100 mm and then its horizontal dimension is equal to 12 mm. So from here I am going to take the section. So from here to here it is 120, total is 120. So I only need this part, the web part. So it is equal to 120 minus this 10 and this 10. So it is equal to 120 minus 20 will be equal to 100 mm and the width is equal to 12 mm. So therefore it is 100 into 12 comes on to be 1200 itself. So next is the third rectangle which is having the width of equal to 180 and depth is equal to 10 mm. So it is equal to 180 into 10 comes on to be 1800. So if I just sum up all these three areas, I'll get the total area of the overall channel section as 4200 mm square. So since it is in mm, so area will be in terms of mm square. So this is all about calculating the areas of the individual structures and then summation of these areas in order to get the area of the overall channel section. So coming on to the next step is that we need to determine the individual centroidal distance with reference to the horizontal and vertical direction. So coming on to determination of the individual centroidal distance as in case of the vertical direction. So in order to determine the individual centroidal distance with reference to the vertical direction, so I am going to take the horizontal as a reference axis, that is the x-axis. So therefore I just start from the first rectangle, this one. So it is nothing but the distance of this centroid with reference to the assumed axis in the horizontal direction. So this is nothing but the overall depth of this rectangle is 10. So half of that will be 10 by 2 and this distance is equal to 100 and the depth of the third rectangle is equal to 10. So it is 10 by 2 plus 100 plus 10 comes on to be 115 mm, 115 mm. So coming on to the next rectangle, it is a second rectangle wherein the depth is equal to half of this overall depth. So overall depth of the web part of the rectangle is 100. So half of that will be 100 by 2. So plus this remaining distance, it is equal to 10. So it is 100 by 2 plus 10 comes on to be equal to 50 plus 10, that is equal to 60 mm. So last one is the depth of the third rectangle from this portion. So it is the overall depth, as we know that it is equal to 10 mm. So half of that will be equal to 5 mm. So therefore this is all about calculation of y1, y2 and y3 with reference to the individual centroidal axis. So next coming on to determination of product of AY. So here I need to determine the product of AY in order to compute the overall centroidal distance in the vertical direction, that is Y, capital Y, for the overall channel section. So therefore I know what are the values of the respective rectangles which we have computed in the previous slide. So for the first, we know we had calculated it as 1200, and also for the second is 1200, and third it is 1800, which we have computed, and y1, y2 and y3 also we had computed as 115, 60 and 5 mm. So if I just multiply that, I'll get the area into y, that is product of A and y. So for overall structure, I need to add all these three AY values for the individual rectangles, so that I'll get the overall AY for the C section as a whole. So it is nothing but sigma AY, that is 219 into 10 power 3 mm cube. So it is in terms of mm cube, because A is in terms of mm square and Y is in terms of mm. So the overall will be mm power 3. So if I want to determine the centroidal distance of the C section as a whole in the vertical direction, so it is given by the formula Y is equal to sigma AY divided by sigma A. So sigma AY, I got the value as 219 into 10 power 3. Sigma A, I got the value from the previous slide calculation as 4200. So if I just substitute and get the value, I'll get the value as 52.14 mm. So 52.14 mm from this axis, from the bottom axis. So this is how we are supposed to calculate the centroidal distance in the vertical direction for the structure as a whole. So coming on to the determination of the individual centroidal distance in case of horizontal direction. So we know that in order to compute the centroidal distance as in case of horizontal direction, we are going to take the vertical axis as a reference. So this is a vertical axis. From here we are supposed to calculate x1, x2 and x3. So if I just start from the first rectangle, so this is the centroidal distance for the first rectangle. So we know overall width is equal to 120. So half of that will be equal to 120 by 2 comes on to be equal to 60 mm is the value of x1 for the first rectangle. So the second will be equal to the 12 mm is the width of the second rectangle. So half of that will be equal to 6 mm. That is the x2 distance from the y-axis, assumed y-axis. So as in case of x3, it is overall distance is 180. Half of that is equal to 180 by 2. That comes on to be 90 mm, which is the value of x3. So after computing the value of x3, so we are supposed to determine what is the product of sigma AX. So sigma AX. So sigma AX, we know the areas of the individual rectangles and x values. So multiplying with the respective values, I'll get these values as AX for the respective rectangles. So in order to determine that for the total C section, so I need to sum up these values, these three values of the individual rectangles, so that I'll get the overall sigma AX value as 241.12 into 10 power 3. So 241.12 into 10 power 3. So in order to compute the x, capital X is nothing but the centroidal distance of overall C section, with reference to y-axis, which is given by the formula sigma AX. So this is sigma AX. So sigma AX divided by sigma A. Sigma AX, I got it as 241.12 into 10 power 3. Sigma A, from the previous slide calculation, I have got it as 4200. So therefore, after all simplification, I get the value of X as 57.4 mm. So this is how we are supposed to determine the value of X and Y for the overall channel section. So with reference to the respective reference axis. So coming on to the determination of individual moment of inertia for the individual structures, that is Ix. So Ix, in order to determine Ix for the individual rectangles, so I have a formula of BD cube by 12. So if I just take the first section of the rectangle, into consideration, for this first rectangle, the horizontal dimension represents B and vertical dimension represents the D value. And for the first rectangle, it is 120 and 10. So comes on to be 120 into 10 cube divided by 12. So therefore, Ix value for the first rectangle is equal to 10 into 10 power 3. Similarly, for the second rectangle, horizontal dimension is 12, vertical dimension is 100. So if I just calculate that, it comes on to be 1 into 10 power 6. So for the third rectangle, 180 is the horizontal dimension, vertical is 10, so comes on to be equal to 15 into 10 power 3. So this is all about calculation of Ix, that is moment of inertia Ix for the individual rectangle. So if I want to compute the moment of inertia Ixx about x axis for the overall channel section, I have to use the parallel axis theorem. So which is nothing but sigma Ix plus AT square. So wherein T is nothing but capital Y minus Y, wherein capital Y represents the centroidal distance in the horizontal direction for overall C section, and small y represents the centroidal distance in the vertical direction for the individual structures. So therefore, for the Ixx will be summation of all the three rectangle terminologies. So if I just start from the first rectangle, it is Ix1 plus A1 into Y minus Y1 the whole square in particular for the first one. Similarly for the second and third. So if I just simplify all the things, I'll get the value of Ixx as 9.84 into 10 power 6 mm power 4. So this is how we are supposed to calculate moment of inertia as in case of XX direction for the channel section as a whole. So coming on to determination of moment of inertia as in case of Y direction. So we are first going to compute for the individual rectangles. So it will be equal to dB cube by 12. These are the values of the dimension for the rectangles which we have. So if I just substitute that, I'll get these values 1.44 into 10 power 6, 14.4 and 4.86 into 10 power 6. So I have to make use of the equation as Iyy is equal to sigma Iy plus At square. So which is by the application of the parallel axis theorem. So here T will be equal to X, capital X minus X, small x. So capital X represents the distance of the centroid with reference to horizontal direction, and small x represents the distance of the centroid of the individual rectangle. So therefore if I substitute all the things, I'll get the value as 11.4 into 10 power 6. So 11.4 into 10 power 6. So here we are supposed to determine what is the value of the least radius of gyration. So compared to Ixx and Iyy. So Ixx we got the value as 9.84 into 10 power 6. Iyy we got the value as 11.4 into 10 power 6. compared to Ixx and Iyy value, Ixx is the least moment of inertia for the overall channel section. So in order to determine the least radius of gyration, I need to consider the least moment of inertia for computing this value. So therefore I need to consider it as K minimum. K minimum is nothing but the least radius of gyration. Always radius of gyration is represented by the symbol K. So is equal to under the root Ixx divided by sigma A. In general it is I by A, but as in particular with reference to this numerical is concerned, it is equal to Ixx divided by sigma A. So if I just substitute and simplify, I'll get the value of K minimum or least radius of gyration as 48.405 mm. So this is how we are supposed to calculate the least moment of moment of inertia as in case of X and Y, and also least radius of gyration, which is provided by using calculated by taking the least moment of inertia in concern. Thank you for watching. Please like, share and subscribe the video. Thank you.